In this video, I want you to imagine that you are driving around a curve and we want to take a look at the vectors that emanate from your point of driving. So for example, you'll have one vector that goes forward, and that'll be the velocity vector. And suppose in this example, the velocity vector is 1, -3. Associated with any kind of movement around curves is also the normal vector. In this case, it will be -3, -1. Now, imagine you are the driver of that object. As far as you're concerned, your view consists of forward and backwards and left and right. So in this situation, when you're viewing yourself, say you're at this spot, the forward direction here might be considered your velocity vector, because as far as when you're driving, if you look straight ahead, you're going straight in the direction of that arrow. And then if you're going around a curve, of course, you have a normal vector that points inwards towards the center of that curve. So in this case, and notice now, these have taken on more of a role of the standard basis vectors. So the standard basis for R2 is the set 1, 0, 0, 1. What I want to do is take the vectors that we actually have, and I want to do something like this to them. I would like the velocity vector to point straight ahead, and I want the normal vector to point left or right as needed. The velocity vector could be backwards if you're going a negative velocity, or simply going in reverse. But right now, this is what I'm concerned with. Now I want a driver's view basis. So here's what I want. Instead of my vectors being this one and this one as my basis vectors, I want them to be the velocity vector, which was 1, -3, and the normal vector, which is -3, -1. This is what I want for my basis. So the first coordinate tells me which direction I'm headed, and the other coordinate gives me left and right. Now, how do we make that happen? Well, we have, based on the standard basis vectors, we have the following equations. If I take and make this new basis into a matrix by putting the columns in like so, if I multiply it times 1, 0, I'll get the vector I want, 1, -3. Similarly, if I take that same matrix and multiply it by the second coordinate, or by the second standard basis vector, I'll get the other vector, -3, -1. So let me give names to all of these things. This matrix here, we're going to call P sub B. This vector right here, it's the velocity vector, but it's the role I would like it to play after I make my transformation. So the velocity vector with respect to B will be in this direction, which I'm guessing this is actually left or right because it's pointing in the x direction, but nonetheless, still I want to make this transformation. And of course, this vector right here is the velocity vector. Similarly, there you can recognize the PB again, and then this here was the normal vector with respect to this new basis, and of course there was the normal vector. So the equations, let me go to these equations here. Of course, each of these equations can be reversed, and I can solve them for VB in the following format. I can take and invert that matrix, and it is, if you calculate the determinant, I'll get -1 minus 9 will be -10, so it's non-zero. And same goes for the other one. And so these will reverse those. Let me go ahead and put the numbers in then. For the first equation, let me call this equation 1 and equation 2. For equation 1, we have B in relation to the B basis. Let me put in the numbers. I already know this number is 1, 0 for VB. PB inverse, I just mentioned that the determinant was -1/10, so we put that out front. Well, it's -10 actually, so we put 1 over the determinant out front. The inverse of a 2 by 2, you remember you swap entry 1, 1 with entry 2, 2. So I get a -1 in the 1, 1 spot and a +1 in the 2, 2 spot. And then you take the negatives of the 1, 2 and the 2, 1 entries. And the velocity vector was 1, -3. For the second equation, we had 0, 1, I guess I'll remind you underneath, this was N, B, and that equals -1/10, -1, 3, 3, 1, times -3, -1. You can multiply these out and see that they work. So what this does is now it makes our first vector is 1, 0, and the second vector is 0, 1 in this new system. This is where they were before. Now let's see what happens to some vector and see what it gets transformed to underneath of this thing. So let's let x equal 7, -4. Determine x under this new basis. So the equation that we have then from right up above, remember that's PB inverse times x. So let's put these numbers in. Well, this one I can't put in until I do my calculations. That PB inverse, what we have? -1, 3, 3, 1, and times x was 7, 4. And let's multiply it all out. So I have -1 times 7, that's -7, plus 3 times -4, so I get -19. And then for the second entry, I'll get 3 times 7, which is 21, minus 4, which will be 17. Let me go ahead and multiply this in and go to decimals for the purposes of this example. Now, this is the value of x with respect to this new basis. And I want you to understand how this actually works. You have, take your 7, -4, and do 1.9 times the first basis vector was 1, -3, and the second basis vector was -3, -1. Watch this work. You got 1.9 times 1 minus 1.7 times -3. This works out to 5.1 plus the 1.9 is 7. Then if I take 1.9 times -3, I get -5.7 plus 1.7 will give me the -4. So notice the numbers here. That 1.9 that's up here, that's that coefficient there. That -1.7 is the coefficient there. So these numbers give the coordinates in the new bases. And notice this is basis vector 1 and basis vector 2. So we're going to want to keep track, or at least keep them ordered throughout what we're about to do. So this is the gist of what we're going to do, changing coordinate systems from the standard to a new basis. So let me do some examples to illustrate the idea. Suppose on this basis, suppose my vector with respect to the basis is given by the following coordinates: -4, 8, -7. Determine x. So the way this works is this guy here is in the B basis. So this represents the coefficients, if you will, or the weights, as I've seen some books call it, that we give to each of the vectors in the basis. So the way we have it is x will equal -4 times the first basis vector plus 8 times the second basis vector, and then finally -7 times the third basis vector. And then you can see what I'm talking about here. Here, this weight or this coefficient is attached to the first of the list of basis vectors. It's first in its position in the vector. Then we have this coefficient, second in the list of the vector items, attached to the second vector in the basis. And finally the -7. -7 is the last entry in the vector, and it is attached to the last basis vector. And then it's just a matter of multiplying these all out and adding them up to find this value. So we have negative 4 times negative 1, so I get 4 plus 24, that's 28, minus 28, I get a 0. Then we have negative 4 times 2, that's negative 8, minus 40, so we're negative 48, plus 49, I get a 1. Then finally 4 times 0 is 0, 8 times 2 is 16, minus 7 times 3, so I have negative 5. So there is x. Another example, let's go reverse here. Given x equal 40 in r squared, determine the representation of x with respect to the b basis. So as before, I need to give you a b basis. Let me do that. B equals 1, negative 2, comma, 5, negative 6. So to convert this, remember, we have this equation. We have 1, negative 2, 5, negative 6 times x sub b equals x. So I'll put in what I don't know and solve for what I do know, or reverse what I just said. So in order to figure out this thing, given an x, I have to multiply both sides by the inverse of this matrix. So the first thing I need to do is calculate its determinant. When I multiply the 1 times negative 6, I get negative 6. Then I'm going to add to it 10. So that's 4. So 1 over the determinant is 1/4. The inverse of the matrix, we swap the 1, 1 and 2, 2 components. And we take the negative of the other 2 components. Let's multiply it out. Here, I'm going to do something real quick. You can put this scalar in front of here, or I can put it on the end of here, or if I want, I can put it in between. So to make my life a little bit easier, just for right now, I'm going to take this 1/4 and multiply it to that vector. Well, it makes this multiplication very simple. So there's our xb is negative 6, 2. Now notice something. Let's go back to the original vector x, which was 4, 0. And x sub b equals negative 6, 2. Now go back to the original vector 4, 0, and I'm going to use these are my coefficients for the representation here. The first vector was 1, negative 2. And the second vector in our basis was 5, negative 6. Let me just make sure this all works out. I'll do the second component because it's a 0. 12 minus 12 is 0. Negative 6 plus 10 gives us our positive 4 like we have here. Once again, notice this negative 6 right here gives the first coefficient, and this 2 right here gives that coefficient. So basically, it tells you what these are coordinates, but now these are not just the standard basis vectors, these are in terms of some other basis. Let's do another example. This time my basis will be in R3. We have 1, 0, 3, 2, 1, 8, 1, negative 1, 2, and at this time x will equal 3 times negative 5 times 4, and your job is to find the B basis representation of this vector x. So one thing we already know, well, this is the equation that we give, PB x b equals x, but we want to find x sub b, so we're doing x sub b equals PB inverse times x. Well, the PB is very simple. You just take these basis vectors and make a matrix out of it. So this x sub b will equal the inverse of that matrix, 1, 0, 3, 2, 1, 8, 1, negative 1, 2, times 3, negative 5, 4. Don't forget this is the inverse of that matrix. Now what I'm going to do is use the adjugate to get the inverse of this matrix, but the first thing I need to do is get the determinant of that matrix. So the determinant of this matrix, let me see, 1, 0, 3, 2, 1, 8, 1, negative 1, 2, that equals, what I'm going to do is expand along the first column. Since I have a 0, it gives me a little bit less work to do. So I have a positive 1 times, and don't forget, sort of the thing that I do, what's typically done is this is the item that I'm choosing for this number out here, but then you cross out the row and cross out the column, and the entries you have left are the ones that make up your the little determinant that you'll be taking. I forget what they call this thing. So that'll be a 1, negative 1, 8, 2, and then minus 0 times something. I really don't care about that part. But then plus 3 times the last part. So this is the item, this is the entry. Cross out the column and cross out the row, and you're left with 2, 1, 1, negative 1. So let's see, I have 1 times 2 will be 2, plus 8 will be 10. I don't care about this thing. Now over here, I'm going to have negative 2 plus negative 1 will be negative 3. Well, this is very nice. The determinant's equal to 1. Now to get the inverse, 1, 0, 3, 2, 1, 8, 1, negative 1, 2. We have to do all these classical adjoint things. I have to do 1 over the determinant, which is 1 over 1. And then to get these inverses here, remember this, the C11 term will be a 1, but it'll be positive because I'm in the 1, 1 position. So that, for this entry right here, the 1, 1 position, I'll cross out the column and the row like normal, and I'll have 1, negative 1, 8, 2. Suddenly realize that I'm going to need a lot more space for this, so I'll not even finish it just yet. And then in the next spot here, this here is position 1, 2. What we want over here is position really 2, 1. So let's go to 2, 1, which is the 0, right? And do the same thing, cross its row and cross its column, and you're left with 2, 1 and 8, 2. But we'll get a negative here. Continuing here, this here is the 1, 3 component, so I really want the 3, 1 component, which is here. So cross the column and the row out, and I'll have 2, 1, 1, negative 1, and it's positive. All right, moving on then. Typically this here is the 2, 1 position, but I'm interested in the 1, 2 position up here. This will get a negative. Remember, these negative and positives, they alternate. So let's see what we have here. The 1, 2 position, if I go down and cross out that column and also cross out that row, what's left? A 0, negative 1, 3, 2. The next entry will be positive. And in the middle rows, you don't have to swap because the entry that's in the 2, 2 spot, if I swap the rows and columns, I'm still in the 2, 2 spot. So cross out its row and its column, and what's left? The 1, the 1, the 3, the 2. You might have guessed it, the next thing gets a negative in the front. And typically, this is the 1, 2, this is the 2, 3 position. So I want the 3, 2 position, which is this guy right here. So cross out its column and cross out its row, and what's left is the 1, 1, 0, negative 1. And then finally I'm ready for the last row of this inverse matrix. Normally this is the 3, 1 position. I want the 1, 3 position, which is this guy up here, and cross out its column or its row and its column. You'll be left with 0, 1, 3, 8. And notice it gets a positive because the thing around adjacent to it was a negative. This next entry will get a negative. Of course, the last entry will be positive. All right, this normally here is in the 3, 2 position, so I want the 2, 3 position. That's this negative 1. So let me cross out its row and its column, and I'm left with 1, 2, 3, 8. And then lastly, the 3, 3 spot, cross out its column and its row, and I'm left with 1, 2, 0, 1. And let's calculate what we get. For this one right here, we get 2 plus 8 will be 10. Then here we get negative 4. Well, I'll put the negative on in a minute. 4 minus 8 is negative 4, but that negative makes it a positive 4. Here I get negative 2 minus 1 makes it negative 3. Then here I get positive 3, I'll put a negative. The next, I get 2 minus 3 will be negative 1. Here I'll get negative 1, that 0 is the other way, negative 1 times the negative will be a positive 1. And then this one here will be 0 minus 3. And this here will be 8 minus 6 will be normally 2, but that'll be a negative 2. And last, I get 1 minus 0 will be 1. Now the question gave us this. They gave us x equals 3, negative 5, 4, and they want the b version of that vector. So I'll put a big question mark here. Well, the equation, as we have, was PB inverse X. That's equal to the B basis version of X. So let's see what we have here. There's my PB inverse, so let me throw that in here. And throw my X in. 3, negative 5, 4. And let's go ahead and multiply it all out. I'll get a 3 by 1 vector. Let's see, I'll do the first row times this column. So 10 times 3 is 30. 4 times negative 5 is negative 20. So 30 minus 20 is 10. And then I'm going to subtract 12. So I get negative 2. Now for my second entry, second row here, negative 3 times 3 is negative 9. Negative 1 times negative 5 is positive 5, so I'm at negative 4. And then 1 times 4 will be a 0. And then finally this last one, negative 3 times 3 is equal to negative 9. Negative 9 plus 10 will be 1. Plus 4 will be a 5. As a check, let me make sure that this vector is represented. This is the representation of this vector. So how we do that is the following. Take the original vector, 3, negative 5, 4, and it should equal negative 2 times the first basis vector plus 0 times the second basis vector plus 5 times the third basis vector. And let me put in my basis vectors to see if this does check out. So I have negative 2 times, what was basis vector 1? That was 1, 0, 3. And then plus 0 times this next basis vector, which was 2, 1, 8. Plus 5 times this last basis vector, which was 1, negative 1, 2. And let's just make sure it does work out. I need to end up with a 3. Negative 2 times 1, that's negative 2, plus 0, plus 5 does indeed give me the 3. Then I have 0, 0, negative 5, there it matches that. And then finally, negative 2 times 3 is negative 6, plus 0, plus 10 will give us a positive 4, and it does check out. So the most important thing is this. And notice the vector x sub b, well there's our negative 2 right there. There's our 0. And there is our 5. So this gives the coefficients in front of the basis vectors. Now that you have the gist of what we're doing, let's get into some of the theory. So I'm going to let B equal B1 up to B sum n. Then PB will look like the following. The matrix with the B's for columns. So the equation we're going to be working on is the following. This is the basic equation, is this. but we're more often than not going to be working with this equation. So that's the gist of what we're going to be doing. So let's start with a theorem. Let B equal B1 up to Bn be a basis for a vector space V. Consider the function T from V into Rn given by T of x equals the vector x but represented in the B basis. So that's the coordinate mapping that this is here referred to as the coordinate mapping. If you'll notice these xb vectors, let me come back go to our examples. Look at the xb vectors. Right here, this vector is in R3. If you look at the previous one before that, it was in R2. That's why we have these things going into Rn. So this creature here lives in R to the n. Now, what we have then is T is a linear transformation that is 1-to-1 and onto. Let me give a proof of this. And I'm going to explain what the terms mean as we do them. So T is 1-to-1. What that means is the following. If T of x equals T of y, then x equals y. Let's prove that that's actually true. So what we're going to do is suppose that x equals c1 b1 plus dot 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 plus cn bn. Remember the b vectors b1 through bn do form a basis, so this is possible to do for any x in the vector space. And also I'm going to let y equal d1 b1 plus dot 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 plus dn bn. These are any two vectors in the vector space. Now suppose also that T of x equals T of y. I want to show that x is equal to y. So if that's true, well, T of x is equal to this thing, which is x represented in the B basis. And over in the other one, we have y represented in the B basis. To be very complete about this, I'm going to replace x with what it equals written out in terms of those basis vectors. Do the same for y. Now, this mapping simply assigns to each of these vectors the coordinates. These are the coefficients. So on the left then, we have C1 up to Cn, and on the right, we have d1 up to dn. Well, two vectors are equal if and only if their coordinates are all equal to each other. So what this tells me is that c1 equals d1 and all the way up through cn is equal to dn. Well, I guess then I think you could see that c1 b1 plus up to cn bn equals d1 b1 up to dn bn. I mean, they're attached to the same vectors, and they have the same coefficients. So therefore, this follows. This then means that x is equal to y. So therefore, this is a shorthand notation for 1 to 1, 1-1. So we've got that. Now, the next thing I want to show is that t is onto. That means, so for any x in Rn, there is, I don't know, some vector v in V with t of x equal to that vector v. Now if the vector v equals, let's say a1 up to an, then if you make x equal to a1 b1 plus, so you apply those as the coefficients, then when I take x and look at its b basis representation, I'll get those coefficients right back. So this particular x will be the one I'm looking for. So therefore, t is onto. So we have onto and 1 to 1. Now next we want to show t is a linear transformation. So basically, what do we want? We want to show t of x plus y equals t of x plus t of y, and if c is a scalar, t of cx will equal c times t of x. So I want to show those two things are true. So what we can do is let x equals, what did I do? C1 up to Cn, C1, B1 plus goes up to Cn, Bn, and then y equals D1, B1 plus up to Dn, Bn. And then when I do t of x plus y, that'll be t of C1, B1 plus dot, dot, dot plus Cn, Bn. So there's the x vector plus the y vector. And inside of the big parentheses, we can combine like terms. Well, the coordinate mapping is just going to strip off those coefficients and send it to the following vector, C1 plus D1 all the way down to Cn plus Dn. Of course, according to vector addition, now keep in mind this is in Rn. So according to vector addition in Rn, I can break this up as follows. But the first vector, this C1 through Cn, is nothing more than x represented in the B basis, and the other one is y represented in the B basis, and that is t of x plus t of y. So it's got that part, the addition part of it is down. Now then, if C is in R, then T of Cx equals, I'll multiply the C to each of the components, CC1B1 plus CCNBN. And of course, that's going to send it to the vector CC1 up to CCN, because those are the remember, this mapping strips the coefficients off of the basis vectors and puts them into a column vector. Well, according to our rules of vector or scalar multiplication, I can pull the C out front, and I'll get C1 up to Cn. And of course, that's just C times T of x. So it's a linear transformation. What that means, this means that V is the same as a vector space as R to the n. So basically they're called isomorphic. V is isomorphic to Rn. Essentially V and Rn are exactly the same. And that's sort of the idea behind all of this, is once we have a basis, let me back up a little bit here. Once we have a basis, they all kind of act the same way. So this is a long way I got to go, but I want to find my original B basis. There it is right here. So just like in Rn, we have the first slot, second slot, all the way up to the nth slot. Well, when you're talking about these vectors, B1 will be the coefficient in front of B1 will tell us what's in the first slot. The coefficient in front of B2 will tell us what's in the second slot, all the way up to the coefficient on Bn will tell us what's in front of the nth spot. Note, T from B to Rn, where you send the vector x into xb, is called the coordinate mapping. From B to R to the n. As an example to illustrate this, I'm going to look at the polynomials with degrees less than or equal to 2, and I claim that that's isomorphic. to R3. Well, let's take a look. Let's call this the solution. The standard basis of P2 is B equals 1 comma t squared. Then what we're going to do is let t go from P2 into R3 by t of x equals xb. Now notice the following. T of 1 is the same as t of 1 times 1 plus 0 times t plus 0 times t squared. So its coordinate mapping will be 1, 0, 0. Capital T of lowercase t is t of 0 times 1 plus 1 times t plus 0 times t squared. So its coordinate mapping is 0, 1, 0. And finally, t of lowercase t squared is the same as t of 0 times 1 plus 0 times t plus 0 times t squared. Actually, 1 times t squared. So its coordinate mapping is 0, 0, 1. So with that in mind, if I take a t of a plus bt plus ct squared, then its coordinate mapping will be a, b, c. And you can see that at the very least that this is going to be onto, because if I choose any vector a, b, c in r to the 3, then I definitely got some vector from P2 that maps to it. Now how about 1 to 1 and that kind of stuff? So if you have t of, let's say, a1 plus a2t plus a3t squared, and that somehow equals t of b1 plus b2t plus b3t squared, then you'll get a1, a2, a3 will equal b1, b2, b3. And you can see that from this it's 1 to 1. I really don't need to go over these. We did it kind of in the theorem anyways. But I just wanted to show you how some of these things work. And it should make sense if you think about it. Let's take a look at P sub 2. The vectors in P sub 2 basically look like this. Any vector in P sub 2 looks like this. And all I'm doing is stripping the coefficients, or the weights, as I've heard some books call it. These weights, A is a weight, B is a weight, and C is a weight. These weights go in the corresponding slots into the vector in R3. So it should make sense that these things do act like each other from vector space, from a vector space viewpoint. They're the same thing. Another example to illustrate the power we're getting at here. Determine if C equals 1 plus t squared, 1 minus t squared, 1 plus t is a basis for P sub 2. Well, since I have this previous thing as an isomorphism, I'm going to instead think of these vectors as vectors in R3. So when I take a look at the 1 plus t squared, you'll notice that's 1 plus 0 times t plus 1 times t squared. Well, its standard basis, remember, is 1t squared. So let me put that down, standard. We'll call that b. So that means when I do 1 plus t squared b, it's going to look like 1, 0, 1. And then similarly, 1 minus t squared in the b basis is going to be 1, 0, negative 1. And finally, the 1 plus t in the b basis is the same as 1, 1, 0 because there's no t squared term. So now all I got to do is consider a matrix with these columns in it. So let's take a look. It's our PB matrix actually. PB equals 1, 0, 1, 1, 0, negative 1, 1, 1, 0. I shouldn't have said PB, that is not actually what it is. But that's the representation of these vectors in the B basis. So what I'm going to do is determine if this matrix is invertible. So then I'll have that the items are 1 to 1 and onto, or in a more vector space oriented way. By showing this is invertible, I'll be able to show that the vectors are linearly independent at the same time as showing that they span, because this is a 3 by 3 matrix. The easiest way to take the determinant, the easiest way to determine if it's invertible is take the determinant of this, and I'm going to go according to the second row because I'll only have one non-zero item. That means, here's the way I do it. I consider items here with a plus sign, then a negative sign, then a plus sign, and then adjacent to it will be a negative sign. So I'll have negative 1 times the following submatrix. So remember, when you do this, cross out this row and cross out this column, and be left with 1, 1, 1, negative 1. So what's that equal? Well, here I'll get negative 1 minus 1 will be negative 2, times that will be a positive 2. Well, since this does not equal 0, the matrix is invertible. So it has linearly independent columns that span. Therefore, C is a basis for P sub 2. Let B equal 1 plus t squared, t plus t squared, 1 plus 2t plus t squared. And you can assume that B is a basis for P2. You can check it out yourself, convert those to column vectors and see what happens. But the problem at hand is to find the following vector: 1 plus 4t plus 7t squared. Well, probably the easiest way is the following. Recall this. Remember the two linear transformation items. So with our thing, we can do 1 plus 4t plus 7t squared. I can break it up into the following. And this, of course, is with respect to the basis B. So if I can figure out each of those components, those are the standard basis components there. And this is our new basis. So this is why it's important to me. These are the standard basis vectors in there. Remember, standard basis So that's why we might break this up in the following format. Now, if I can find each of these items, I'll be set. Well, you have basically, this gives us a matrix here. If you look at 1 plus t squared, I'll think of as the vector 1, 0, 1, because I have 1 times 1 plus 0 times t plus 1 times t squared. And then t plus t squared will be 0, 1, 1. And finally, the last one, 1 plus 2t plus t squared will go to 1, 2, 1. So my PB matrix one, 0, 1, 0, 1, 1, 1, 2, 1. And what I want to do is find the XB, that's what I'm trying to find here, my vector, the B representation of this particular vector. So this is where we've come up with the equation PB X B is equal to whatever the vector was originally. So in the matrix notation here, well, before I do that, let me rewrite it this way. So PB inverse, let me first do that. Well, let's do the determinant of PB. I'm guessing the best I can do probably along the first row, I guess, because I do have a zero entry. I can do the first column, but I think I'll do the first row. So I have 1 times, so I'll cancel out the row and the column. I'll be left with a 1, 2, 1, 1. Plus 0 times, I really don't care about that part. Actually, it's a minus 0. Remember, the signs alternate as you go along. And then finally 1 times, and then cancel this row and cancel this column, and I get 0, 1, 1, 1. So let's see what we get here. I get 1 minus 2 is negative 1. Over here, I get another negative 1. That's minus 2. So I know the thing's invertible. Well, that's nice. And well, of course it has to be, because since it's 1 to 1 and onto as a function, that means the function is invertible, which automatically means that the matrix is invertible. So I should have known that anyways, but to do part of the computation, we need to figure this out anyways. So if I want to do PB inverse, first thing I have to do is to divide by the determinant and then go and figure out the items in my inverse matrix. So starting with this, remember we're going to do the same things here. I'll start with this 1 here, its cofactor that I'm going to be looking at. I will cancel this row and this column, and I'll get 1, 2, 1, 1. And it's assigned a plus value. The next one has a minus value in front of it. And the way you do this, this is normally the 1, 2 spot. But when I look at this matrix, I want to go to the 2, 1 spot, which is here. There's 2, 1. Cancel its column and its row, and you're left with 0, 1, 1, 1. And the next one is positive. This would normally be the 1, 3 position, but I want to go to the 3, 1 position, which is right here, and give me a crossed out row and a crossed out column, and I'll be left with 0, 1, 1, 2. Moving on, the next position, this is normally 2, 1, so I want to go up to the 1, 2 position, which is right here, cancel its column and its row, and I have 0, 2, 1, 1. It's a negative because it's adjacent to a positive. They alternate in sign. The beautiful thing is 2, 2 is normally the 2, 2 position. Well, when you flip 2 and 2, you still get 2, 2. So this is the spot I'm looking here, the cofactor for this particular position. Let me cancel out its row and its column, and I have 4 1s at the corners. And then this spot right here is normally 2, 3. Let me go to the original matrix and find 3, 2. So 3, 2 is this guy right there. Cancel its column and its row, and I have 1, 1, 0, 2. Of course, it gets a negative. 1, 1, 0, 2. And then the last spot here is typically 3, 1, but I want 1, 3 in my original matrix. There it is right there. There's 1, 3. Cancel its row and its column. We have 0, 1, 1, 1. And it gets a positive. Now the next one here, this spot right here, is 3, 2. So let me go to the original matrix and find 2, 3. Row 2, column 3 is this guy right here. There's 2, 3. Cancel its column and its row, and we're left with 1, 0, 1, 1. It gets a negative. And finally, the 3, 3 spot will also be the 3, 3 spot for both of these. So cancel its row and its column, and I'm left with 1, 0, 0, 1. And let me go ahead and now complete my matrix and compute all of these determinants. So for this one, 1 minus 2 is negative 1. Don't forget this negative here. I get 0 minus 1, so I get negative 1. That negative makes it a plus 1. Here, 0 minus 1 makes that a negative 1. And here we got 0 minus 2, negative 2, but that negative makes it a positive. Then 1 minus 1, that zeroes out. Here we get 2 minus 0, but that negative, we get a negative 2. And then we have 0 minus 1, I get negative 1. Then I get 1 minus 0 is 1, but there's a negative there. And finally the last entry is just 1. I'll leave the negative 1/2 out there. It really doesn't matter much. Now then, we want 1 plus 4t plus, what was it? 7t squared. Now the standard basis for this makes this look like a 1, 4, and a 7. So that's what I'm aiming for as far as changing it to all of these. Remember the formula, x b equals pb inverse x. Okay, we want 1 plus 4t plus 7t squared, which instead of that we're going to use 1, 4, 7. I'll put it down there like so. And that's going to equal negative 1/2 times, let's see, negative 1, 2, negative 1, 1, 0, negative 1, negative 1, negative 2, 1. And the x that we're looking for was the 1, 4, 7. So let's see what it equals. I'll keep the negative 1/2 out there. Of course, I'm going to get a 3 by 1. So let's start. I'm going to get negative 1 times 1 will be negative 1 plus 4. So I'm at 3 minus 7. Looks like negative 4. And then the 2, 0, negative 2 row, I'm going to get 2 minus 14. It looks like negative 12. And then finally, for the last row, I'm going to get negative 1 plus negative 4. I'm at negative 5 plus 7 will be at a positive 2. Well, this is nice. I'll get 2, 6, negative 1. Another example. This time I'm going to let b be the basis 1, negative 4, comma, negative 2, 9. This is a basis for R2. For x in R2, determine a formula for x b. So what I'll get then is x b will equal, let's call this the solution, will equal pb inverse x. Well, the pb that we're talking about is really right here, 1, negative 4, and negative 2, 9. And let me replace x with xy.